Well, hello, everybody. Oh, are we doing the recording? We are. We're doing the recording, in which case, let me share my screen and let's get started. Where is IntelliJ? There it is. All right. Aha. Beautiful assembly code. Great. And I'm just going to go up top to where I have some nonsense and we will see. We'll get started with a little bit of introduction. Simulator. And where am I setting my initial registers? There I go. Great. Let's make this wider and that narrower. Cool. Even though this, unfortunately, this assembly simulator is not complete, but that's no matters. We're going to start with some pretty things and then go into increasingly degrading resolutions as there's also a terminal simulator, which is complete but uglier. So yeah, today we're going to write some assembly code, kind of. So much of what we've been doing lately, we were just doing sort of a Zio from scratch series, right? Where we were writing this language, this sealed trait in Scala terms, this data structure, algebraic data type, whatever you want to call it, this grammar for a language, the language of Zio. And we were interpreting that in this fiber runtime thing that we made, right? And we basically compiled in a sense, or transpiled or transformed, whatever you want to call it, that data representation, this description of operations, into a lower level representation. It wasn't machine code that we turned it into, but it was threads and fiber refs and maps and atomic booleans and all sorts of stuff. A lower level than certainly the nice, beautiful, high level Zio constructs. Generally, that's how it works. Generally, you do not compile into a higher level syntax. So and that kind of pattern of going from this beautiful high level structure that describes some abstract domain elegantly into something else is what we do all the time. Sometimes that's called compilation, but really there's nothing. Compilation is just a fancy word for when generally the output of a function from A to B, where that B is really low level, or maybe it's like machine code or assembly. And then if it's another language, we tend to call it transpilation. So if you take some Scala code and turn it into JavaScript functions, well, we tend to call that transpiling. But all the piling, however we call it, it's really just a function. Maybe I should take some silly notes, right? So it's just so much of what we do in programming, and the beauty of functional programming is that like so much is just captured by this simple A to B arrow, right? So when we have a sort of a language and we turn it into machine code, maybe the alias for this kind of function, some abstract syntax tree, or sometimes we call it an intermediate representation. We call this compiling. Whoop-de-doo. But it's just a function from something a big data type to something a little maybe more something less powerful, something more powerful to something less powerful, in some sense. Obviously, the goal of this in computers is to actually, maybe I shouldn't say less powerful, because ideally this machine code representation should be runnable such that it has the same semantics. It really gives the semantics to the language that we're writing, right? We're writing Scala. Scala gets turned into Java. Java gets turned into JVM bytecode. Java gets run on the JVM. The JVM sometimes decides to, when the hotspot JIT compiler decides to, it'll turn it into machine code and then finally run that on whatever your processor is. It's just all these steps of lowering to something until you finally hit the bottom. And that's kind of where we're going to start today. This is kind of what today is about, hopefully. I'm sure some of you are more well-versed in this domain than I am. I do not have a computer science degree, so I've sort of been trying to, in fits and starts, over the years, backfill some of my ignorance on these matters. I did not take a compiler's class. I've heard of the Dragon book, but I haven't read the Dragon book. But these things are on my to-do list. But there is this wonderful book called Elements of Computing, NAND. I think maybe it's more colloquial known as NAND to Tetris. Elements of Computing. It's going off the screen. NAND to Tetris. And this book is really good for me. I say all the time, in these things, we do it all the time in these things of building these pedagogical models, these simplified versions of things, to just sort of unearth, get an intuition for the core techniques, and then kind of hand wave away, all the extra complexity of real world implementations, because it's just, take your core idea and just run it through time and contributors and edge cases, and then you get the real thousands of commits of whatever, the Linux kernel. But the core idea is really what's important, and it gives you kind of the confidence that you could maybe build something like whatever, like a Zio, like a programming language, like a compiler, like an effect system, whatever. So these pedagogical models are very nice. And Elements of Computing is all about that. They start with you building sort of NAND gates, so a not and gate, right? So if it's basically just a Boolean operator. So true, true. Well, that's false. Yes. Really, everything that's not and is true, right? So and would usually be true if true and true, but it's kind of like saying, B1 and B2, and then nodding that. So that's this NAND gate. It's a machine. It's an electronic logic gate. Works with transistors. It's kind of a black box to me, unless you understand, I don't know, electrophysics and whatnot. But it's actually doing something. And that's kind of what computers are built out of, or it theoretically could be the base logic gate out of which all of these, the rest of the logic gates that are used to build computers can be built out of. It's this fundamental piece. And it's a really cool book where you basically, starting with that, you build up this, wire all these NAND gates together, and you build other more complicated gates until you build essentially a CPU. And then you build some machine code that runs on that CPU. And then you build an assembly language that transpiles or compiles into that machine code that runs on that CPU. And then you end up building a virtual machine and sort of a Java-like language on top of that. So you get this whole breadth of computing, and then you build an operating system kind of. Obviously, not that none of these are production grade, but it's a really awesome book. Highly recommend it. We're kind of going to be using their representation of assembly code, which certainly isn't. There are a couple of popular assembly code, I guess, flavors, RISC and CISC and stuff, and like x86 and ARM. Maybe you've heard some of these words, and maybe you haven't. Doesn't really matter. These are sort of the complicated real world things. We're going to be focusing on something that they call hack, which is a sort of a fake machine that's built to be simple, but still give you sort of this. It's going to be operating on with the same terms, the same nouns, the same verbs, just way simpler than these actual production grade machine languages. But the cool thing is about machine code is generally most of what we do in computers, right, where we're taking these A to B transformations, something complicated, turning into something else, compiling it into another language, perhaps into JavaScript, into a lower level representation. But machine code is kind of the end. It's the bottom. Machine code is just basically a whole bunch of byte arrays. And each byte array represents a different operation. And when you load this particular string of bytes into a memory, wherever your CPU is looking for instructions, and it reads those bytes, that'll actually make it do physical things in the world with electricity. Things are moving. Finally, there's no more program that's interpreting this. It's actually a physical entity that's interpreting it. And these gates were specifically built. These CPUs were specifically built and wired to understand these byte patterns, these bit patterns, and then change in some way that we can. It changes in a deterministic way that we can then interpret back out what the meaning of that thing was. So this is the end of the road, machine code. And assembly code is just one step above machine code. It is basically syntactic sugar for machine code. It's like human readable aliases for machine code. Basically, we're not going to do this now. But on the left side of the screen, this is the hack assembly language, and we're going to talk about a little bit what these different instructions mean. But the first thing to note is that each line here would be would be assembled, if you will, into a single byte string. So on this first line, we have this thing at R0. We don't know what that means yet, but the assembler would take this piece of assembly code, this assembly statement or expression, whatever we're going to call it, and it would turn it into some random, not random, but for all intents and purposes, some ugly byte string that's totally not human readable. And that's what would be run on a hack CPU and actually do whatever this means. What does this mean? Well, this means load some value into the A register. That's what that means. We'll talk about what all these things mean. And then when you actually run this instruction on the CPU, it's going to indeed load some value into the A register. And we're not really going to talk about how that CPU works. That's going to be a black box for us today. But we're going to get down to that level of assembly code at least, and write a little assembler and maybe play with an assembly, a CPU emulator, which will not actually, the CPU is, as I was saying before, the CPU actually runs this physically, but we can always make an emulator in our nice, beautiful Scala high-level language that will simulate interpreting the assembly code, which will give us at least an intuition of what the actual machine might be doing with, transistors and RAM and flip-flop gates and all the other crazy details of CPUs. But we're going to start high level. So let's talk about
of high level.
Sorry?
For some definition of high level.
Yes. Well, this whole exploration it was always entertaining to me that I think on like I don't know, I read some C programming manual or maybe it's on Wikipedia, it describes C as a high level programming language. And coming from, starting in Ruby and Ruby on Rails and moving on to Haskell and Scala, I was like, what? What, that high level? What is it? Is this a joke? But at the time, it was incredibly high level. It's just a few steps above assembly code. But yes, computers. The history of computers has a lot of names that quickly have become outmoded by just the passage of a few years. So yes, generally you shouldn't name things with a relative adjective because it will.
And Scott, you've been working on creating your own computer, right? It looks like you've had a picture there from very, very low level on the mechanical side. So maybe we got to have you on here to do one of these, and we'll put this together. We'll see if Kit stuff will run on this.
Yes. We'll make the machine code, and then you can take it the rest of the way. That sounds super fun. Okay, so I hope some of that made sense. That was just a big sort of contextual dump. I'm still in the process of learning this myself, so I'm just going to give you my best understanding of it. Then again, sometimes the best time to teach is right after it's sunk into your head. So please feel free to ask me any clarifying questions if I sound crazy, and I'll be very honest if I have no idea what the answer to your question is. Okay. So let's actually switch over to another tab. This is a pretty emulator of some machine code. Alas, I did not quite finish adding all my register values. So while this is doing something, we cannot see the very important bit of what is in the register values. Even though actually, let me just do this real quick because this will be very pretty. I can not very pretty, but prettier than where's my view? Here we go. Emulator view.
I'll add drama. Which is great.
Yeah, I love adding drama. I love it. So emulator view, let's say signal dot map, and we'll grab out the A register. Oh, emulator var dot signal dot map. We'll get the A register to string.
And this is using laminar, right?
This is using laminar, and I've been working on my own little weird actual like Swift UI wrapper around it. So technically, it's using that as well. So we have A register, and then we're going to have the D register.
Yeah.
Thank you.
And we did some videos on the past on laminar doing some front end stuff with that, so you can look back at that if you want to.
Yes. And I'll just make these dim. So okay, now it's all good. All right. So it's not all good, but it's something. So there we have. Now we have in way too big of a font compared to everything else, our A's and D registers. So now we can kind of tell what's going on and talk through this program. So what are the components to this CPU emulator? It's kind of what this is. It's a CPU emulator that is interpreting this assembly code. Now, in the real world, this assembly code would have been assembled into binary strings and then loaded into an actual CPU that would be running these mechanically. But here's our simulation of this. So here's our program. which is basically just these are indices starting at 0 to 15, but these would be mapped into memory somewhere. So in RAM, you would have some sort of location in memory that says, here's where my program starts. And then if you offset that by 1, that'll be the next instruction, and then the next instruction. So kind of just an array of instructions. With hack in particular, every instruction, I think one of the simplifying patterns that they followed or rules that they gave themselves is that each assembly instruction maps to a single sort of 16-bit, so basically 16 bits. Every assembly instruction turns into 16 bits. It's a 16-bit computer. Today, most of our instructions are way bigger and we have variable amounts of instructions. But in this case, very nice and simple. If this were actually assembled, you'd see for each line 16 ones and zeros instead of a nice, slightly nicer word. Okay, so we'll kind of just go through this a couple times to familiarize ourselves with what's going on. So our CPU has a couple of registers, very simple. Basically, these are just variables. We have a variable called A and a variable called D. And these would be, registers are very easy to access. They're very fast in the CPU. They're just like generally very few of them, way fewer than you have RAM or cache or anything like that. And they're expensive to construct, and they can just be accessed near immediately. So they're good for just storing little values that you're operating on. And then you have RAM, which is generally a little slower, but it can be way bigger. So that's what this horizontal axis here, and these are also indexed from 0 up until 23, just so it's not, we don't have a lot of RAM, but we want a simple program. And so each of these addresses would be pointing to basically a 16-bit chunk of code. Actually, I guess in this case, 32-bit because I'm using Scala ints, but whatever. Each of these memory addresses would be storing, 16 zeros and ones. So every 16 bits, these would be pointing to. So we have our instructions that are in RAM somewhere else, and we have our RAM here. And then we have 2 registers, and that's kind of it. That's all our computer really has in terms of memory and registers. So these 2 special variables, and then just random access memory that we can store whatever we want in. So what the heck are these 2 things up here? A and D, they have strange names. Why not A and B or something else more descriptive? Well, I guess that's just them following the conventions of assembly code and CPUs, is that as you go lower level, things become more ancient and less friendly. The beauty of high level languages is that over time, we have evolved to sort of give nice method names to things. And Zio, we like to think of really nice descriptive method names and have conventions. But then again, it's also easy for these new libraries to quickly change their APIs. Zio, we can come up with a Zio 2 and say, okay, we'll change your code here. Zio 1 was only around for about a year, so everyone wants the fancy new thing. We'll update it. It's not going to ruin the world. When you're writing a machine code and specifying this, literally, you can't change that. It's the CPU that's been shipped out into the world. They really can't ever change this. And then it's just technical debt accrues and accrues. So it seems like a relatively awful eldritch language most generally. So there's this, I think maybe the hardest part of learning all this stuff, and I tend to keep learning it. But from what I could tell so far, trying to learn LLVM and x86 and ARM and all that stuff, is that you're going to have to do a lot of reverse engineering of conventions and names, because nothing's going to help you. Nothing's just going to be obviously true. You just have to look at a bunch of examples and sort of create a mapping and an intuition for yourself. So, but generally, it's probably simpler than it seems beyond all that noise and mess. It's just not helping you. That's generally what I found with all the computers. People are just really bad at naming and explaining things. So, okay. So we have these 2 registers, A and D. They're just variables, but they're kind of used conventionally and a little bit magically by the machine or in specific ways. Really, you could just put anything you want into register A or register D, but they have a couple of special features, particularly A. I'll say what they both stand for. So A stands for address or addressing register. That's because of one way it's used. D stands for data. This is generally what stores the actual data we're using. So we see this instruction here, the first instruction, it starts with an @ sign. At kind of looks like an A, doesn't it? Well, what this instruction is going to do is it's going to load whatever value is after the @ sign into the A register. So every line that starts with an @ sign is going to load whatever is after that. Now, what the heck is R0 then? Well, R0 is just an alias for the number 0. It's a pointer to the 0th element in RAM. So really, it's just 0. But when you're writing assembly code, it's nice to be able to give meaningful names to things instead of just 0 and 1. We can also have this thing here that says output first. Now, we could just have had a number here pointing to the 10th instruction. It could have just been @10, but we used a label in our assembly code. So output first down here actually is just an alias for 10. So when we say @output first, it's actually going to load into the A register the number 10. So we're just always loading in an int into these A and D registers. Theoretically, we're just a series of bits, but mostly an int. So R0 is just a handy alias for 0. So when I run this instruction by hitting the space key, we'll see nothing happen because A was already sort of defaulted to 0. But in case it wasn't, now it's definitely 0. So instruction number 2. This is assembly code. And there are a few sort of, it looks like a nice high-level language, say assigning D equal to M, whatever the heck M is. But there are actually a limited number of these. You can't just do any operations here. This is sort of like a single value here. Like you can't do M times 6 or something. There are a very reduced instruction set of things that actually work. So D minus M works. I don't think M minus D, for instance, or D minus 10. It has to be very specific. But D equals M is its own little instruction. And what the heck is this going to do? Well, for all of these computation instructions that have an equals, it behaves just mostly as we might believe, where the D register is going to get set to something. But the question is, what is M? What could M possibly stand for? We have this register A and register D. What could M be? Well, this is why I said earlier that A stands for addressing register. A is kind of like an index into the array that is RAM. And M means when this instruction is interpreted by the CPU, it's going to actually load from the RAM whatever value is stored at the index that A is currently set at. So it's this kind of two-step process to really just say D should equal RAM at whatever, at 0. So these two lines, because our instruction set is so limited, and because they wanted to give each instruction one line of code, these two lines basically turn into D equals RAM at 0. So really D equals 55 in our case, because that is currently what's been preloaded in to the first register here, the first place in RAM. So I'm going to refresh again, just do that one more time. So first we're going to load into A, this index 0, because we want to load 55 into D, but we have to do it in these two steps. First, loading 0, the index into A. It already was that, so we don't see a change. And then assigning D to the value at that index. So M basically always means wherever in the RAM A is pointing to. Kind of weird. Assembly code isn't fun. It's very low level. Great. So now D is equal to 55. So D started out at 0, but once we say D equals M, now it's going to be equal to 55 because that's what was at position 0 here. Okay, now we load into a R1, which is just, once again, an alias. All these R's are basically just, I think there's R0 through R15 or something. Just aliases for the first 15 points in RAM in this case, the 15 addresses in RAM. Okay, so now it's 1 then. So 1 is now an A. And now what are we going to do? Well, we're going to say D equals D minus M. So we're basically saying that D is going to be 55 minus whatever A is pointing to, 33. So this is just another awkward way of saying D equals D minus 33. And to point to that 33, first we needed to set A to the index of that element. So once again, kind of awkward shuffle. You have to use this A register whenever you want to access RAM. And so now D should be equal to 55 minus 33, which is 22. And now we're going to load something else into to A, which is always what starts with this @ sign. In this case, it's the value of this label. And this label is down here on line 10. So it's basically just pointing to line 10. So we're just going to put 10 into A. 10, A. And why would you want to put the a pointer to now, so far we've been using this address to address into our RAM, but now we're addressing to a point in our instruction set. Why might we want to do that? Well, Juget. Did you get it's a jump statement, right? It's go to. We're in this horrible low level world of jumps for control flow. So this with the semicolon statement, not the equals, is a little weirder. But basically, what this is saying, it's saying jump if greater than. So what does this mean? What is if what's greater than? Let me do this. So D, G, G, T. So we want to, if D is greater than 0, then jump to whatever register A is pointing at. So line A. So once again, almost every instruction needs to have sort of two instructions, really. One what we are sort of in a higher level world, you could say, like, can't this just all be on one line? Well, because our CPU is so limited and every instruction can only be 16 bits, it needs to be two separate instructions. And we kind of have to use A as this intermediary to sort of store some context for the next instruction. And that's kind of really what registers and stacks are all used for storing some context that you just can't do magically. You have to do it in the machine. So first we're saying, okay, point your ship to line 10. And now if the value of register D is greater than 0, then go to line 10. So lo and behold, we should jump to line 10. And we do. Great. And so that line happened to be called output first. Okay, let's see why. So first we're going to load register 0 again. So it looks like we're pointing to this register. One reason for a symbolic alias here, like R0, is that now it's very clear that we're pointing to the RAM instead of maybe, as we've seen, what goes into A can also be a point in our instruction. Pointer to a position in our sort of program here. So now we're going to load register 0. So we're clearly targeting this value for some reason. Great. So it's A is 0. And now we're once again loading into D the value of that register. So 55. Great. And now we're at this line 12, which is also labeled output D, even though we didn't jump there. And now we're going to load into our addressing register 2 for this position in RAM. And now, instead of doing D equals M, we're going the other way around. So we're assigning to that memory location the value of D. So 55 goes there. And now we're in an infinite loop. That's our reward. We're loading up this line, and then we are jumping always, no matter what. That's what that means. No comparison here. Just jump back to this line. And that's basically our program. So what the heck does this program do? Well, this is actually the max operation. So whichever one is bigger here, 55 or 33, that's what's going to be returned at position 2 in memory. So if I run this, we're going to see that, oh, 55 was returned. Great. Otherwise, if I wanted to change this, where am I setting my registers? Here we go. Let me make this 133 or 88. So yeah, let's do 88, please. I have to make another change. No, it goes a little delayed, but good. There we go. So cool. Now, ideally, we'll see instead of 55 here, 89. I'm just going to run it real quick. Yay, 89 is there. And this sort of infinite loop is just a signal to like, halt, stop, you're done. In hack, at least, for some reason. It's hacky. It's called hack, so I'd imagine that's why. Cool. And if we see the difference here, it's basically the control flow is all about, it all takes place in this jump statement. So we set d equal to d minus m, and now it's a negative number. Remember before, when it was 33, we were getting 22, which was positive. But now that's negative, we're only going to jump to d we're only going to jump to output first if d is greater than 0, and d is not greater than 0. So now we're going to continue merrily along, in which case, what did output d do? What did output first do, rather? It loaded the first address into memory and then set that to d. So it put 55 in d. Well, what happens if we continue merrily along? Well, now it loads R1. So it's basically going to load 89 into d. And that's what it does. And then we're going to, now this time, go to output D. We're going to jump down here. So we have to skip over this other code path that we took before, because now otherwise we would just sort of load 55 into our data register. So now we have to skip. And there we do the same thing. So yeah, this bit takes care of putting the value of whatever's in D into register 2, and then ends the program. And then we have these two options that come after this jump. We can either load R1 into memory, or we can load R0 into memory. And if we do load R1 into memory, then we have to skip loading R0 into memory. So that's basically the whole control flow of the program. So if it's greater than 0, we're going to do this jump. And obviously that's just it's going to take whichever code path and load whichever value here is bigger than the other one because of the subtraction. So that'll determine which one's bigger if it's greater than 0 or not. Anywho, hopefully that simulation is a little helpful. I also have an ASCII flavor of this simulation. I'm not sure if that's going to be any different though. But we can write our own assembly language now and sort of think about how we might do this from the beginning. Okay. Any questions?
I don't think we have any questions. We have some cool comments. Phil Allen was sharing some details that last time he did something like this, as well as a hardware implementation of object-oriented programming principles in this thing called recursive from the 80s. So there's some cool trivia stuff there.
All right, that sounds incredibly cool. I will check out those comments later. So yes, the last, where's this other thing? I have one more looping thing. Loop, where am I looping? Loop emulator, there we go. Okay, so yes, this is essentially the same thing except in ASCII. So I'm not sure if it's terribly interesting, but yes, now we have everything in ASCII there. Yeah, so it's just the same thing. Okay, cool. So I have gotten my JavaScript version, and I think it's maybe a little more useful here. The only difference here is that we're sort of saying, there's the symbol table saying, where do each of these, what do these names mean? So output first means line 10. Output D means line 12. Infinite loop means line 14 of our program. So we'll just jump to that line. Okay, great. But let's do this all from scratch. Maybe that'll help. Or maybe it won't, but it'll be fun. Hopefully it helps. So we'll just sort of build a little DSL or at least an abstract syntax tree for our assembly code. ASMast. I'll just call it ASM though. So yes, this is going to be our assembly language. And from this, we could actually write an assembler that's poured out binary code to be run on some machine. But for now, we're just going to create the language and maybe do some other stuff. We'll see. We'll see how much time we have. But hopefully that was at least an okay explanation kind of how assembly code might work in this very simplified version, where you have one hand tied behind your back, or maybe you have both hands tied behind your back, and all you can do is kind of chew your way out of problems. You do not have many tools that you're used to at higher level languages. But the beauty is all these higher languages somehow, magically, it might seem, turn into something like this. Great. This is, Turing complete, even though unfortunately we probably want a little more RAM to do anything interesting, but okay. Let's get started. So what do we need? Well, we had these, first is always good when building one of these things, these ASTs. It's just like, think about the grammar of your language. So we had this Let me turn off Copilot as well. I don't feel like cheating today. So we had these things. So we can sort of load some kind of value. And that could be either a number or a register. So I could have R1, R0. I could make my own name. I could say, cool. That actually has a special convention to it. If it's not sort of a special named register, so sort of R0 pointed to the address 0 in memory, R1 to address 1, et cetera, et cetera. But if you just have your own name that isn't special, my name, these values are supposed to start being mapped at address 16. So the first 0 through 15 are just all R's here. They have special aliases. But if you give an alias that is not a special one, it's sort of been pre-decided, well, then you're going to get mapped up to 15. So my name would become this. Or maybe I'll just make it X. And then if somewhere else in my assembly code later on I had Y, that would be mapped to position 16 in memory. So in your assembly, you can kind of give things semantic names, but one of the jobs of the assembler is to just basically map those into deterministic locations in memory. And if I refer to X again later on, it's not going to also assign it to location 18, right? It's going to make sure that it's still pointing to the same one. So it's one of the jobs of the assembler. Actually, let's quickly look at some assembly code because we didn't quite look like this in my program. So this is actually what would be written and parsed. So this is it's a language, and you need the assembler to do something to this. One of its jobs is obviously to just parse this into some kind of representation that can be converted into binary codes. But the other important job of it is to create a sort of a symbol table of these special names. So, well, R0 just gets mapped to 0, R1 to 1. But when it comes across output first here, we don't really know yet, is this a variable or is this a label, right? Are we trying to point to some special value on memory 16, location 16 and above, or are we about to do a jump statement? And this is probably therefore going to be a position in our program. And basically what you can do is you can write this label down here. So this is the nicest thing you have in terms of developer productivity in assembly is you can make labels. But this is not going to connote to an actual runnable instruction. It's just going to basically give a meaning to the use of that label previously. It's going to say, hey, output first is going to point to this line of code. Wherever this line of code ends up landing, we don't want to have to calculate that ahead of time. Imagine if you didn't have this, then when you're writing assembly code, you'd have to basically count the number of lines.
110.
Yes, go to line 10. And then if you added some lines here, you'd have to update everything. So that's truly an awful experience, obviously. So they added labels. They were like, fine, we'll add labels. Probably they were reluctant to. But then they did it. They're like, fine, we'll add that feature. That's the only quality of life, really, thing that you get in assembly code. And of course, the ability to have variable names. So you don't just have to memorize like, 18, have some comment up top.
Go to line 18.
Oh, line 18.
I always rely on for when I have a tough problem I need to crack.
My tough variable. But yeah, that would be awful. So you could just say, whatever you want. And then the job of the assembler is to just give that a number and remember it and make those replacements before translating everything to binary code or to our CPU emulator, I guess. So yeah, those are really the 3 jobs of an assembler, is to give you those couple bits of syntactic sugar and then just to handle the parsing and of course the translation into binary code. So basically each of these lines would get replaced with the binary meaning of whatever these things meant. One something or other. Can't have a 2 or a 3 in there. That would be cheating. But so that's the job of the assembler. Anyway, and I guess it'll also in the parsing ignore comments. So that's something that's nice. Cool. So we have these 3 kinds of instructions. We have this load A, if you will. That maybe it would be nicer if that's what it were called, but it has this just symbolic alias, the @ sign. Obviously, in parsing, it's kind of arbitrary as long as you're consistent. We could have done anything. It could have said, we could have written load into AX. That could have been as long as we consistently parse it to mean the same abstract syntax node. Doesn't really matter, but for whatever reason they chose at, then either an identifier or just a plain number. Okay, so that's the first sort of piece of our grammar, this load A, and it has these two flavors, either sort of a symbol or just a value. And then there are a couple more. There is the sort of compute or store, maybe compute and store. And that looked something like, if I go back to the browser, D equals M, D equals D minus M. So whenever you have the equal sign there, D equals M, D equals D minus M. And you'd think that, oh, we have to parse some, a special math language here, make our own complicated expression parser here for these operations. But no, you don't. There are only a few of these things valid. And so, as I mentioned, you can't do M minus D. It's just D minus M, M, and I think there are like 15 or 16 of these. It's probably 16. It's probably a power of 2 valid computations that you can do that all operate on either A or M or some constants like, D plus 1. Some things you might want to use, very convenient. And anything else you want to do that's more complicated than that, well, you've got to sort of go back and forth between the two registers, right? Like, what if you did want to say D plus 15? Well, then instead of that, you're probably first going to want to load 15 into A and then do D plus A. So a couple steps. Great. So that's the compute and store. And obviously this can change as well. So maybe we're going to do D plus A and store that into memory. So yeah, this is kind of its own little segment. We probably want to make our own sealed trait just for this bit, because for any of them, you can either say store it into A, store it into M, store it into D, or any combination of those. MDMA. No, you can do anything you want with these. Oh, Adam. A. There we go. Cool. So that's the language there. We have sort of our destinations. On the left-hand side, the register or this kind of pseudo register M that actually assigns to RAM, and then we have the computation. Great, so that's node 2 of our grammar, and then node 3 is the jump, which is something like this. We have a register, or actually I think a computation, and then we have sort of the jump statement. So jump greater than. So in this case, if D is greater than 0, then jump to whatever is currently in the A register. So this with jump, it's always sort of a two-step dance with the A register, where first you have to load the destination, and then it will jump to the destination only if the value here satisfies whatever Boolean predicate is associated with this jump statement, of which there is a set amount. Greater than, equal to, less than, greater than or equal to, etc. Great. And JMP will always jump no matter what, and therefore it doesn't matter what the output is. So generally you'll see 0 there. I guess they could have done this, but I guess to make it consistent, usually it's this, but it probably could be anything, because it will be ignored. And I think that's really all that matters. So yeah, this is a sort of a computation, and then a jump expression. And so, yeah, what can go here? Well, I think it can be any of these computations. Yes, it can be. It can be anything that can go here. So we want to use the same parser, the same abstract syntax tree node subtrait to represent these computations, because they could be used in 2 places. Great. Cool. I think even theoretically, you can have both of them. But that's insane, and I haven't seen that in any of their example programs. But I think that's a specification of their CPU, so maybe that would be smart to do. But nah, that seems just very crazy. No one would want to read that. Okay, cool. Well, let's quickly actually do something. Great. So yeah, we have these 3 things. Let me maybe pull it down so we can. Oops. Go into our companion object and make some actual values. Great. So let's see. Let's start with load A. So load A. Well, basically that @ sign, we don't need to remember this. This is just for parsing. What really matters inside is the symbol or value. And symbol or value, I've said the word or. So maybe we can make another trait called, I guess I'll just call it value here. And it can be either a symbol, which will be a string, yes, extends value, or it can be a, I guess an integer, int extends integer. It's hard to come up with these names here. I guess I kind of wanted to call it value. Let me just call it symbol or value then. Symbol or value. Oh, nope, almost there. Symbol or value, symbol or value. Cool. Maybe I'll make my code a little smaller. Hopefully that's okay. So yeah, not my favorite name, but we're just going to go with it for now. So it is descriptive. It is descriptive. So there we go. That's the first syntax node in our tree. For compute, we have sort of the registers, the destination, which is a set of some kind of register, and we can just make that really quickly as well, which is going to be register A, D, or this sort of pseudo register M that basically means whatever RAM at A, but good to know. So we have a set of registers, and then we have a computation. Computation. There we go. And this needs to also be its own set of things. We could turn this into its own special DSL where you have like adds. It could be, you know, computation, left-hand side and right-hand side or something like that. But really, as mentioned, there are only a set number of computations. It is not composable by our normal standards of composable DSLs. So I'll just throw in a couple here. Actually, maybe I'll have, yeah, there's definitely 0, and there's 1, and there's, you could just get the value of B, value of M, value of A, and then there's D minus, D plus A, D minus A, etc. D minus M, D plus, there's plus and minus for both of them, and there's other stuff as well. But for now, we'll just focus on these. And then maybe if we're trying to parse something else, we'll add some more. Great. Okay, so that's just a set of registers and a computation. So we have that. And then finally, and this needs to also extend ASM. And then we have a jump clause, jump, which takes a computation and then a jump expression, which I'll make that a jump expression. Not the greatest names, but that's okay. So jump expression, and I will just have Copilot fill these out because I think it's pretty smart. No, almost pretty smart, and added a $sign there, but otherwise pretty good. So yeah, now we have this seal trait hierarchy that matches exactly the only kinds of abstract syntax trees we really care about, which is pretty nice. And then we have a couple of options. Maybe the more interesting one, we could write parsers for this and just actually parse the language. But the other thing we could do is just kind of make a CPU emulator. Why not that? There's actually some stuff we'll have to do beyond parsing. Oh yes, I forgot. There is actually technically one more thing. And this is where compilers and parsers have so many options available to them. We're kind of taking this functional approach using sealed traits, which is very nice. The recommended interface in the book is very Java-y and quite awful, and does not use parser combinators or anything. It's a very mutable affair, and does not seem very fun to write or work with. I would use, and in fact, in the other file where I've done this, use ZeoParser, and that was a very lovely experience. And I'll post this code later, and if you want to take a look at those nice little parsers. But I think it'll be more interesting to write a CPU emulator very quickly. And potentially, the other thing that we needed to deal with were these labels. So technically, that's part of the abstract syntax tree. It's not meaningful when actually evaluating the program. We should pre-process and evict those from the actual instructions, because they're not going to emit any binary code on the computer. They're just going to sort of change the meaning of our programs. Really, we want to eliminate all symbols, eliminate these and replace them with either their labels or come up with addresses in memory for them if they're variables. So that kind of pre-processing step. But and this is kind of where there's always this awkward balance when writing these kinds of things where, and I wish there was a perfect solution, but there's really not, where you have these ASTs, you've written this AST and it's great, but using it in another context, you kind of don't want a couple of the nodes anymore. We don't, when we actually run this thing, we don't want label or symbol to still be there, but there's no great way of doing this where we just eliminate those. You could do recursion schemes maybe to handle this in some weird way. You can also just duplicate the whole sealed trait hierarchy, one for an earlier step, one for a later step. And I think, people like to be dry. That probably, if you're actually building an industrial compiler, probably the way you want to go. Even though there's a lot of balance between them, they have a different sort of purpose, and you kind of want to transform mechanically one into the other. So at that second stage that you've definitely processed all the symbols. For now, if we've forgotten to process a symbol, we can just blow up and just kind of treat it like these two nodes have dissolved from our program later on. But that's always kind of an interesting bind design-wise to find yourself in.
Which I think is what they do in the actual Scala 3 compiler. I think there was some discussion about this.
Oh, really? They just hope that it's not there anymore? That's been
you have, it's a little bit like we do in the Zio runtime, right? Where you say this is an invariant, we have to maintain that this is well typed, but it's not reflected at the type level there. And yeah, you have a guarantee of if you're at this compiler phase, then this node no longer exists, but it's kind of the same tree regardless.
And with a tree as complicated as Scala's, I could imagine why they don't want to have 10
different versions of
that are slightly different, because that's awful. Programs that work on one wouldn't work on the other if you have some general methods. So it would be great if there was somehow, maybe a future language will have this idea of slightly munging a data type, but that's cool to know that that's what they do there. With a language as simple as ASM, maybe we can get away with duplicating it. Depending on the context, it's always different. But we'll steal it from the Scala compiler and just invariance, use invariance, the guarantee. Cool. That sounds totally reasonable. Okay, so let's quickly write a CPU emulator because we've got time for that, right?
6 minutes.
We have 6 minutes. So first of all, we need RAM, right? So that's the thing that we saw over here. We need RAM. We just need some addresses here. What else do we need? Well, we need an A register and a D register. We also need our program. So let's just add all that stuff. Also, what do we need? We need a sort of a pointer to where we are, a program counter, which is kind of a secret special register that our CPU will have. I'm not showing it here. I'm just it's implied by which line is green. Clearly, there's some state that knows which line we're currently executing. So the program counter, the A register is an int, D register, program counter, and then we have the program itself, which should be I guess I'll make it a vector of ASM. Great, cool. All right, so let's do something, and we can do a couple things, but maybe one would be to call step. We can just make a function that will just get us the next stage of our CPU emulator and do all of the operations that we need to do. Well, what's important? Well, the first thing that's going to guide all of this is our current program. Our current instruction, inst, I guess I'll call it to be nice and terse. And that's just going to be, we're going to index into our program at the program counter. Great. And now we can match. So this should be quite simple. Symbol should be quite simple. In this case, we've already said that we're going to only match the values. So that's an invariant. If it's not a value here, we're going to blow up. So we'll deal with that in a second. So this is going to be the value that we want to load into A, which would be quite simple. So all we do is copy the program. We copy the A register is going to be equal to the value. And then the program counter is going to be program counter plus 1. So that's A, pretty straightforward. And if we get anything else here, no. We're just going to throw a new, I'm going to see what symbol not found, no. Or a symbol should have been evicted, whatever. Symbol bad, good. Cool, and we have a label, which is also, we're just going to throw, this is an invariant. Labels should have been processed by now, my dude. Okay, so two exceptions down there. I'll move these all towards the end because they're ugly. And what else? Okay, so now we have to compute things and jump. Can we do any of these? All right. So for computation, we need to process this in two different places. So this is probably something we can pull out into another helper method. So I'll say comp result equals process computation. Let's throw that into my made up method, use some IntelliJ magic to make a function, and this should get us back an int, right? Everything gets us back an int. And we can just say computation match exhaustively and then deal with the awful patterns. So it's really quite self-explanatory, a register. So now we get to sort of see the semantics we were talking about. Well, what is M? M actually means RAM at a register. Quite straightforward. D plus A, well, that's going to be D register plus A register. D plus M is going to be D register plus the RAM, et cetera, et cetera. I'm just going to let Copilot figure these out and just double check it. Yes, so M is always RAM at A register. Cool, we could even pull that out into our helper if we felt like it. But that's basically process computation. Pretty great. So that's the result there. And then we want to store it in the registers here, which are a set of registers. Now, there's no great way of doing this because they're each a different value pointing to this object. Unless we wanted to sort of do some dynamic dispatch, we're just going to have to handle each one separately. So if register contains register dot D or A, well, then we want to say, here, I'll say this, val next D. It's always fun to do this. So maybe the one downside of functional programming sometimes is this becomes slightly awkward. So next A, if the register that we want to assign to contains A, then we're going to say, well, that's going to be the result of the computation. Otherwise, we're just going to keep the old A register value. And same with next D. So if it contains D, then we're going to do that. That next RAM, if registers contains register.m, well, then we're going to say ram.update, and we're going to update at the A register with the comp result. Because right, we're by saving that into RAM, we're saving what was sort of in at address A, the result of the computation. So if it was, once again, M equals D, then the result of processing the computation D is just going to be the value of the D register. And then we're going to take that result and store it, stash it in wherever A was pointing to. Otherwise, we're keeping the old RAM. And now I can easily say copy, relatively easily say copy, and I'll let Copilot just put the registers in the right place. So A gets the next A, D gets the next D, program counter increments, and RAM becomes next RAM. And finally, let's see. In the interest of time, we'll take it over from here. Jump expert, let's pull that in. Let's see if this is correct. So the next programming counter will be yes. Yes, it's going to be A if the computation satisfies the given predicate. So if the computation is greater than 0, then we're going to jump to A. That's our next program counter. Otherwise, we're just incrementing by 1. So that's basically it. And jump is always jumping, so there's no computation. And that's basically, that's our program processor. That's our CPU emulator. Very, very, very basic. It would be cool to use this. So maybe I can, once again, use the magic of, let's see. Actually, there's a version of this that does not have any of the niceties of the labels. So we'll just use that because we won't write the label parsing. It doesn't take that long, but we are at 0 minutes, negative 1 minute. So let's just write quickly, let's emulate something. CPU emulator demo. So let's see, val ASM equals vector of, come on, Copilot, be magical. Oh, I've got to trigger it. Come on, Copilot, just translate it. So you don't need parsers. That's kind of nice. Import ASM underscore. And hopefully that's correct. Let's see. 0, store and D, computation M, 1. It seems to be pretty correct. 10, that's just wild. Jump to 0, 14. Good times. Hopefully that's nice. And now we can say our emulator is going to be the CPU emulator, and we're going to have our ASM, our program, Then we're going to say everything starts at 0, 0, 0, and our RAM is a vector dot fill. Let's just go 24, 0. Great. And now def loop. We will do something in here. What's it going to be? Well, we'll print. What can we print? We'll print. We'll make a nice little message, which will be A is going to be emulator dot A register. D, come on, emulator dot D register. And then RAM, it's quite fun. What am I doing? Let's add some spaces, quickly make it pretty. RAM is going to be our emulator.ram.makeString. I'll just have them be separated by spaces. So we're going to have to count ourselves, or no, not quite. I'll just duplicate it, do a zip with index, or actually rather, how many? 0 to 23 dot map to string, or no, make string space. There we go. And sometimes those go crazy. Do I have any other information? Well, there's the program counter. Let's just do that. I won't actually output the whole instructions. So emulator.program counter. And then we could just sort of look and compare that. So I'm going to first print line our message. And then we're going to, I guess I could just have it do it. No, here I'll say io dot standard in dot read line, just to have us pause, and then we'll loop again. Loop rather with a CPU emulator, and loop with, and this is going to say units. We're going to say CPU emulator dot step. So we're going to print and then change and print and change and print and change. And now it's called loop, and hopefully we can see with our original emulator something somewhat interesting occurring. Basically a simulation of the same program, sends app, run. Great. So here, let's not make this too big, so I can jump up to our program. So the first thing is that we're going to load into A, our symbol or value here, which is 0. So we're going to load 0 into A, which shouldn't change anything. We actually jumped forward 2 instructions. Great. Have I stepped correctly? Oh, you know what? I might not be stepping the program counter. Let's see. Step program counter equals program counter plus 1 for load. Am I not looping correctly? Loop emulator step. I'm referring to this other emulator. Let's just call these all emulators, just referring to the same one every time. Okay, now we'll check. All right, live debug. Okay, seems like it's going to jump forward 2 steps again, which is no worries. So now we're on program counter 1, which is going to set D equal to M, which is just 0. So that's not very exciting so far. Oh, duh. We need some actual interesting values here. If anything interesting is going to happen, remember this is doing a comparison. It's just going to remain 0. Let me quickly copy this. RAM emulator. Or let me just do it here. Updated 0, let's make this 55, and dot updated 1 is 33. And now we can run it, and then we'll finish off. Okay. So loading 0 into A, and then we loaded 0 into A, but it was already 0, so nope, that's a no op. Now we're going to set D equal to M. So D is going to be what was in position 1, and great, I didn't take into account the different sizes here, so apologies, but we're only dealing with these first 2 registers anyway, and I guess the third one eventually. So yeah, then the third instruction, D becomes indeed the value that was in position 0, 55, and so on and so forth. And if I keep going, eventually, I'm just going to keep going, we should see 55 has ended up in position 3. Because it was the larger of the 2 numbers, and then we're just gonna loop infinitely, looping forever.
Most productive way to use your computer.
Now we can halt. All right, well, that's something.
That's awesome.
That's something. I hope that was entertaining.
Yeah, that's really cool. Thanks so much for sharing that with us.
Anytime. I will keep going down this rabbit hole and hopefully have prettier simulations in the future. But that was today's week. I
That
might
was
need a
really
couple of weeks to cook the next bit.
cool.
All
All
right.
right, awesome. Well, thanks so much, everyone, and have a great weekend. And yeah, we'll see you next week.
Okay. Thanks, Adam. Take
Bye.
care, everybody.